Hello ladies and gentlemen. So what we're going to do today on this video is we're going to take a look at the derivative of a product rule. So we're going to look at, instead of taking the derivative of a power function, now let's remember what we know how to do at the moment. We know how to do the derivative of this using our derivative rules. We know that the power function is going to be, the derivative means take the exponent, bring it down, and take one away from the exponent level. Now, that works for a series of single base power functions. So if I had x to the 3 plus 4x to the 5 minus x to the 1/2, I could take the derivative of this by taking each derivative of these terms separately and then adding or subtracting them. That was the derivative of a sum and difference rule, which follows the limits properties of sum or difference, that if I have the derivative of a sum, it's the same as the sum of the derivatives. So this derivative would simply be, and we would write that as or we would write that as, depending if we're comfortable with the half exponents or if we like the radical notation. Okay, so that's what we know how to do. This is different. Now we're going to be able to take, and we're going to take the derivative of a product, two things being multiplied together. Now the first thing that you have to understand is that the derivative of a product is not, I repeat, is not equal to the derivative of the first times the derivative of the second. It doesn't work that way. This is the way it does work. If I have a function h of x that's made up of the product of two things, f of x times g of x, then the derivative of h of x will be the derivative of the first term in the product, times the second term without it taking its derivative, plus the derivative of the second term times the first term without taking its derivative. So in words, the way I would say this is the derivative of a product is the derivative of the first times the second plus the derivative of the second times the first. This is the way that we'll have it in Leibniz notation. You need to get used to it. Remember, this whole thing means taking the derivative. So we're taking the derivative of u times v. So what this is saying is, so the first thing you do is you take the derivative of u in terms of the variable x, then multiply that by v, plus you take the derivative of v in terms of the variable x, then you multiply that by u. This and this are equivalent. You need to be able to read both. Now, once again, being able to say it is the key here. I've been doing this for a number of years, and if you can say it, you can do it. If you try to memorize it by visually looking at it, it's much harder. And it's important that we try to keep the first in the first one and the second in the second one, not for this one because it's plus, but when we do the derivative of the quotient, the order is going to matter. So let's get into that habit now. It's the derivative of the first times the second plus the derivative of the second times the first. Now, there's no reason to stop at only 3 terms. The pattern continues. So this would be the derivative of the first times the other 2, plus the derivative of the second times the other 2, plus the derivative of the third times the other 2. And again, we could keep going. We could have 4 terms, 5 terms, 6 terms. What fun we could have with this. And the pattern will continue. So again, it's the derivative of one of them times the other 2, plus the derivative of a different one of them times the other 2, plus the difference of the third one times the other 2. If you can say it, you can do it. Okay, let's do some examples. So now, this first example, this says to differentiate without using the product rule. So if I'm not going to use the product rule, here I've got a bit of a problem because this is a product. There's f of x, there's g of x. Let's bring this into focus. Is that better? Let's try this. There we go. So there's my first function, there's my second function. So this is set up as a product. I need to express it as single base powers. if I'm not going to use the product rule. So, as single base powers, we need to expand it. The derivative of a sum is going to be the sum of the derivatives. The derivative of 10 is 0, and that's your derivative, and you're done. Now I'm going to be the first one to tell you that's pretty simple. That's pretty nice. Maybe we'll put this in there just so that you know where it came from. You see the derivative of the constant is actually 0. Okay, so that was nice. Let's do it using the product rule now. So this is f of x, our first term. This is g of x, our second term. So the derivative is supposed to be the derivative of the first times the second, plus the derivative of the second times the first. So what's the derivative of the first term? Well, it's a sum, so it's going to be the sum of the derivatives. So it's 2x plus 0. I'm not going to write the 0 anymore. What's g of x? X plus 5. What's the derivative of the second one? Well, it's 1 times f of x. So once again, make sure that you're clear on this. That's the derivative of the first term. That's the derivative of the second term. We expand. We collect like terms. And we get the same result. One without using the product rule, one using the product rule. People are going to argue, at this point, this is a little bit more complicated, more steps. I would agree, but that's not always going to be the case. So we're practicing a new rule that's going to make our lives so much easier in the future. But right now, you're quite right. If I wasn't told how to do this, I could expand it, take the derivative of each individual term, and I'm good to go. That's the beauty of this part of calculus. You're going to have choices. Some people are going to like that, and they're going to flourish with this idea of choices, and they're going to choose the strategy that's the easiest. Others of you are going to have to learn that skill. Let's look at the next one. So what we have here, we do have a product. Let's make sure that we understand that we're looking at a product here. This is my f of x, this is my g of x. So following the pattern, and it wouldn't hurt you to write it out for a little while. F of x times g, f prime of x times g of x plus g prime of x times f of x. It's not going to hurt. Take a derivative of the first one is 2x times the second one. Plus the derivative of the second one. Times the first. Expand. Collect like terms. That is not right. Let's see, that was it right, but I had a 10 and 5, so that should have been a 15. Let's change that. Sorry about that. My brain started to wander there for a little bit. So I've got 6x to the 5 plus 12x to the 5, so that's 18x to the 5. 10x squared plus 5x squared is going to be 15x squared. All right. Now, as you can tell, this is the only calculus step. All of this is algebra. So probably 2 marks for the calculus, being able to get this nice line here, and 1 mark for the algebra. So a 3-mark question perhaps. Okay, here's the next one. And zoom in a little bit. I'm not sure how this is coming out in clarity. Maybe that's a bit better. Okay, so now this is Liebig's notation, and what this says is the derivative of this times this. So this is saying the derivative of a product. So what we're going to do is we're going to, now I can show this to you what this would look like in Liebig's notation. The derivative of the first one would look like this if I was to write it out in a way that says take the derivative of the first one times the second plus the derivative of the second one times the first. And I'm running out of room here. But you see what I'm saying here. So it's the derivative. This is the way we say that. Now if I actually take the derivative of the first, it's going to be 2x minus 3 times x to the 4 plus 2. The derivative of the second one is going to be 4x to the 3 plus 0, because the derivative of a constant is 0, times x squared minus 3x. Do my expansion here, so I'm going to get 2x to the 5 plus 4x minus 3x to the 4 minus 6 plus 4x to the 5 minus 12x to the 4. Okay, and once again, all I'm doing is expanding, okay? Okay, let's collect like terms. So I've got 2x to the 5 and 4x to the 5. That'll be 6x to the 5s. I've got negative 12x to the 4. Oh, and I got a negative 3. So the 12 and the negative 3 is going to give me negative 15x to the 4s. And then I've got 4x, no other x's. And then I've got minus 6. And that would be my final answer. And again, 2 marks for the calculus part, taking the derivative of the first times the second, plus the derivative of the second times the first, and then a mark for the algebra. So about a 3-mark question. Okay, let's see what's on our next sheet. So that's differentiate, 1, 2, 3, 4, and now this is our next one. Okay, so this is a good question. Now, notice what's different here. They're asking us for the derivative at a specific point. They want to know the derivative when x equals 1. What this means is we do not need. Now, there's going to be times when you want to. There's going to be times when we don't. But we don't need to simplify the derivative before we sub in x equals 1. We don't need to simplify the derivative. Sometimes we'll want to, but let's take a look at a case where we might not want to. So here is a product rule. We have f of x, we have g of x. So if we want the derivative of h of x, it's the derivative of the first, 15x squared, plus 14x, plus 0. Plus the derivative of the second, 4x plus 1, 5x3 plus 7x squared plus 3. Okay, do we see what we have here? So this is f prime of x, this is g of x, this is g prime of x, this is f of x. And again, if you can say it, you can do it. There's nothing to it. Hey, that rhymes. I love it. All right, so now look. If I was to expand and simplify, zoom, 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 zoom. Oh my goodness, my head is going to burst. Now, as a grade 12 student, you should be able to do that. There's no problem with you doing that. However, let's think ahead a little bit. They're asking for the derivative when h equals 1, which means every one of these x values is a 1. So I'm not going to expand everything out. I'm not even going to put in the 1. I'm going to say 15 times 1 squared is 15. Plus 14 times 1 is 14. That's going to be 2, 1, and 3. Oh, sorry, 6. This is going to be 4, 1. And this is going to be 5, 7, and 3. Now you've just saved yourself a ton of time. And if this is on a test, and if you're not paying attention, and if you're not going to be skillful with this, your time's going to be a problem. Let's face it, okay? So we need to think about what we're doing with our algebra and our substitutions before we just go ahead and do it. That's part of this course, is starting to decide a strategy beforehand and be skillful with it. So our next step is going to be to take these out to their arithmetic solution. So this is going to be 29, and this is going to be 9, and this is going to be 5, and this is going to be 15, and the whole thing's going to give us 336, and I'm done that question. Relatively easy. However, once again, had you choose to expand that, life is going to be awful. Let's take a look at another case where that might be beneficial to substitute before you simplify. So this is asking for the equation of a tangent. So if I'm going to come up with the equation of a tangent, somewhere I'm going to be using this. And for me to be able to work with that, I need to know the slope of the tangent, and I need a point. Well, lucky for us, they're giving us the point of tangency. This is the point where the tangent line touches the curve. Now, how do I know that for sure? Take that one value and plug it in. It's going to be 1 take away 3 is -2. That's going to be 1 plus 3 is 6. 1 plus 2 is 3. So -2 times 3 is going to be -6. So when I plug in 1 here, I get -6. So this point is on the curve, and it's going to be the point of tangency. Let me draw you a little diagram of what that looks like. I'm not pretending to know what the curve looks like. Okay? Not even coming close to pretending to know what the curve looks like. But let's say the curve does something like that. Let's just say it does. And let's say at x equals, well, see, this is already wrong. My curve has to come down below. So that was a goof. Let me change that. Let me say that my curve does something like that. And now, that is x value, x equals 1. This will be the y value of -6. So this is the point 1 comma -6 on my curve. And as a point of tangency, that's what it means. It's the point where the tangent just touches the curve. Okay, so back to the question. Determine the equation of tangent. This is my original function. This is the curve. This is the point of tangency. This is the value that's going to go in here. So what I need is a slope of a tangent value. How do we get that? We take the derivative. So the slope of the tangent is going to equal y prime. This is a product. Derivative of the first times the second plus the derivative of the second times the first. But now, normally you would go and you would expand all this and you collect like terms, and that would give you an answer in general. But we don't want an answer in general. We want a specific answer. You want the slope of the tangent when x equals 1. So again, 1's going to go in for here. So it's going to be 2 minus 3, which is -1. We're going to put a 1 in here to the 5, so it's going to be 3. Or 1 plus 2 is 3, that's right. 1 goes in here, we're going to get 5. 1 goes in here, it's 1 minus 3, so it's going to be -2. So this is going to be -3 plus -10 is -13. So the slope of the tangent when x equals 1 is equal to -13. That's the value that's going to go up here now. We have everything we need for this equation. So using y minus y1 equals m x minus x1. Y is -6, so put the -6 in. The negative and negative become positive. The m is -13. The x minus x1, which is 1. So now we're going to expand. And you're going to put it in standard form. And that means that the a value in front of the x needs to be positive. So it's coming over to this side. So it's positive 6, -13. Positive 6 minus 13 is -7. And that is the equation of the tangent to the curve at that point. That's the equation of that line. Now, again, I don't know what this curve looks like. I just made it up, and I just threw it in there. Well, so that was question 7. That was question 6. And we have one more question for this. And this one is asking to find the points. Now, that's a different question. Find the points where the tangent to the curve is horizontal. Now, we know that to get a horizontal tangent, you have to have a slope of 0. So horizontal lines have a slope of 0. And that's something that we need to know. And I'll give you a mark just for putting that in. Now, it's also asking for the points. So let's be clear here. I don't just want x values. I want the x and the associated y value. And if I want to look big in my notation, look mature in my notation, That's the proper notation. There is no y in this consideration. There's f of x. That's our function. Okay, so I guess what I need is I need the slope of the tangent. So the derivative of f of x is going to be the derivative of the first times the second plus the derivative of the second times the first. So it's 2x plus 3 times x squared plus 3x plus, did you notice that they're the same term? 2x plus 3, x squared plus 3x. Now I need this in general, so I'm inclined to expand this and collect like terms. But stop. Look before you jump. These are the same terms. Look what I can do here. Beautiful. This plus this means that you have two of those. Now, don't expand at this point. That's in factored form. This is beautiful because what we want to do is we want to set f prime of x equal to 0. And you want to solve for those x values. There's no way I want to expand this. I'm going to be creating work for myself. So I'm going to set these two equal to each other. And I'm going to take a look at what I've got. Now, I've got 1, 2, 3 things here that are multiplying to give 0. So either, there's no way any value of x is going to make 2 0. So that's out of the question. The other way to think about it is dividing both sides by 2. That 2's gone and we still have 0. So that means either this term has to equal 0 or this term has to equal 0. Well, the only way this term is going to equal 0 is that if x equals negative 3 over 2. So that is an x value that will give me an associated y value where the slope of the tangent is horizontal. This one needs to be solved. Well, we're going to factor this. We have two things that multiply to give 0. So either x equals 0, and it doesn't matter what the middle is, or the second one is, or x equals negative 3. Well, it's x plus 3 equals 0, in which case x equals negative 3. So I have three x values that will give me the slope of the tangent of being 0. So the 3 points are negative 3 over 2, f of negative 3 over 2. 0, comma, f of 0, and negative 3, comma, f of negative 3. Now notice I don't put it into the derivative. If I was to put these values into the derivative function, I should get 0. Now it has to go into the original function. And that's going to take a little bit of work for this one. I'll do that in just a minute. This one's going to be fairly easy. Let's take a look at the original function. If I put in 0, 0, 0, 0, so it looks like it's going to be 0, 0. If I put in negative 3 is going to be 9. Take away 9, which is 0. So that's going to be 0. This one over here is going to, so if I plug in f of negative 3 over 2, it's going to be, now these two are the same, right? So I can save a little bit of time if I do this. So it's going to be negative 3 over 2 squared plus 3, negative 3 over 2, all squared. So that's going to be 9 over 4. And this is going to be subtract 9 over 2, all squared. So getting a common denominator of 4, it's going to be 9 minus 18 over 4, which is going to be negative 9 over 4, which is going to be 81 over 16. So this point is given by negative 3 over 2, comma, 81 over 16. And that just took a little bit of algebra down here to do. That's all. Okay, guys, here's some homework here. Practice it up. That's out of your green textbook. And that's a wrap for the product rule.